Thank you, Ishan. I'm happy to be here. I'm going to depart, I think, from the lectures that I've been giving in the workshop, in that this subject matter doesn't have too much to do with the kinetic theory. In the context of the kinetic theory, you can view it as the rare gas limit of kinetic theory. It's work that I've done with Alexandre Valence at the University of Rennes, and I'm going to be talking about how the wind moves sand. Motivation for this comes from the phenomenon of desertification that has a very dramatic example in the Sahara Desert. The Sahara has suffered from about 25 years of drought, and as a consequence of that drought, vegetation that existed to anchor sand and sand dunes has been overgrazed or has died because of lack of water, and vast amounts of sand have been released. And under the influence of the wind, this sand is blowing across the Sahara from the northeast to the southwest. And here's a photograph taken by NASA of sand encroaching upon the capital of Mauritania. And this sand is threatening, of course, areas of habitation here and also areas of agriculture throughout the Sahara. And the idea is that if we better understand it, we can better facilitate ways of stopping the motion of sand dunes, and a better understanding of the physics of sand transport will lead to that kind of understanding. So the idea is that these countries which are plagued by desertification are typically very poor, and what we need are low-tech solutions that will help to anchor the sand. And for example, there was a French engineer in Mauritania that was very successful in protecting roads in Mauritania that were threatened by the motion of sand dunes across them by simply using plastic sheeting to redirect the wind across the dunes in ways that would stop their motion. So a better understanding of the interaction between wind flow and sand motion could facilitate those kinds of solutions. At the moment, the way that the inhabitants of these countries attempt to block the motion of sand dunes is take palm fronds that have fallen from palm trees and insert them at the crest of the dune in order to block the motion of the sand. Okay, so all that's by way of motivation of why we'd like to understand the interaction of the wind and the sand, and try to characterize the relationship between a flux of sand and the strength of the wind. And the mechanism by which sand is typically moving in a desert is a phenomenon that's called saltation. And the idea, well, the saltation comes from the Latin word for jumping. And the idea is that grains jump. And the first grain is picked up by a particularly strong turbulent fluctuation, and then a grain is accelerated by the wind until it finally falls, and by virtue of the fact that it's been accelerated, it has increased momentum, and it hits grains of the bed, bounces off, but in the process ejects other grains, and then too they're accelerated by the wind. Strike the bed, eject other grains, rebound, until finally there's a cloud of grains above the bed, and the cloud of grains slows the wind above the bed, and finally a steady state is achieved between the cloud of grains being accelerated, striking, rebounding, slowing the wind. Okay, and that's the process we're going to be interested in. So primarily this process, And then there are other mechanisms that become important in let's say, more extreme circumstances. When the wind speed gets higher, then direct suspension of grains by the turbulent velocity fluctuations of the wind play a role in keeping grains suspended. And let's see, and when the number of grains above the bed becomes large enough, then grains collide not only with the bed, but they collide with one another above the bed. And then that cloud of colliding grains is more like the dilute gas of a kinetic theory. There's an additional mechanism of momentum transfer associated with those collisions, okay? Okay, so that's the situation. And what we'd like to do is we'd like to obtain a continuum description of that motion. That is, we'd like to specify the wind, the velocity of the wind as a function, and I'm going to be dealing with situations that are steady and uniform in this direction. We'd like to describe the profile of the wind as a continuous function of the vertical coordinate. And similarly, the profile of the particle velocities as a continuous function above the bed. And will represent, let's say, the distant shear stress of the wind as a quantity that is located at some height above the bed, this height being the height at which the concentration of particles becomes vanishingly small. And by way of notation, I put hats on variables that I imagine have dimensions. And when I take the hats off, that means I've made those variables dimensionless. And let's see, and there are two parameters, essentially one. There's something called a friction velocity that says something about the strength of the wind. So it's a quantity with dimensions of velocity that is created from this distant shear stress of the wind divided by the mass density of the fluid, of air. And then there's another parameter that has to do with the particle properties, and that's the ratio of this distant shear stress in the wind to the weight of a layer of fluids 1 diameter in thickness. So this is a measure of the weight of the grains relative to the strength of the turbulent shearing flow. Let's see, and we'll be talking about air drag of the wind on the grains, and we're going to characterize the drag coefficient in a usual way. There's going to be a form drag, form drag, which gives rise then to a quadratic component to the force on a grain, and a viscous drag. So mu f is the viscosity of the fluid. T is a measure of the fluctuations of the grains, and I think everything else has been identified. Okay, so that's what we want to do. Now let's say by way of additional motivation, I want to show you a film taken in a wind tunnel of the phenomenon that we're interested in. Okay, so this film has been slowed by a factor of 60. Is that visible to you? Can we get the lights a little dimmer? Can we turn off lights? I think I've got it on a continuous loop. So we watch it for a while, and you'll get. And I'll talk about the phenomenon of interest. And what about this light? Okay. So let's see. This is taken in a wind tunnel. The grains are about 0.3 of a millimeter in diameter. They're rounded sand, so they're not perfectly spherical. We're seeing the flow illuminated with a laser sheet, so particles will pass in and out of the sheet as they move normal to the flow. And you may the typical motion of a grain is this jumping motion. You will notice some collisions between grains taking place above the bed. But the collisional interaction, by and large, is with the grains coming down from their jumping ballistic trajectory and hitting the grains and scattering other grains. Okay? So I say this is saltation. Finish with the film. Yeah, it is, and we're not going to be taking into account the rotational motion, but it's there. Okay, so first I'm going to talk about experiments similar to what you've just seen, carried out in a wind tunnel. And this is, so the French group that participated in the experiments, and the wind tunnel itself was built by geological scientist at the University of Aarhus in Denmark, Kjeld Rasmussen, and it involves a section of about 18 meters. It's a long wind tunnel, and fluid is sucked from this point through the wind tunnel, and the turbulence is enhanced by having some roughness elements here that will provoke the more rapid development of a turbulent boundary layer, fully developed turbulent boundary layer, and sand is fed into the tunnel. Now, this is a rather unusual facility, I should say, because most people who run wind tunnels would rather not have sand put into them. Okay, so this wind tunnel was made exclusively for the purpose of studying wind-blown sand. And there's a working section where both the flow of the sand and the flow of the particles are steady, roughly, and uniform. That's what I mean by fully developed. So the variation is only across the flow. And the measurements are made of the wind speed, and a laser sheet is used to assist in the visualization of particles. High-speed cameras are used to take the pictures of the particles, and then all of that data is reduced and converted into profiles of the wind velocity and the particle velocity and the concentration profiles. Okay, so and that's more or less the data that we'd like any continuum theory to predict. And for example, here is data. And this is data on volume fraction, or concentration, at various values of the friction velocity. Okay, these should have hats over them because they're dimensional. So we have 5 values of the strength of the turbulent shearing flow that we're dealing with. And for each of these, the profile of the concentration has been measured. And the striking thing about these profiles is they all, and this is a log scale, they all seem to be exhibiting an exponential decay with a decay length that is identical. So that's interesting. So that the decay length is 40 particle diameters. Okay, so keep that in mind because that's going to be an important parameter to test the theory against. What else can I say? Notice that there's a difficulty in getting data very close to the bed. Very close to the bed, the concentration of the particles is high enough so that it kind of washes out the signal. The signal is so bright you can't distinguish individual particles. So data is taken, now I should say, these particles are about 1/4 of a millimeter in diameter. So we got 4 particles to a millimeter. So we got about 20 particles here at the lowest point at which we have data, and we've got about 40 particles here, kind of at the midpoint of where we're gathering data. So keep that in mind. that not all of the concentration can be resolved, not all of it down to the bed itself. Okay, so that's one piece of data. And I could show you profiles of the velocity, particle velocity at this stage, but I'll reserve that for when I'm making comparisons with the predictions of the theory and those profiles. Okay, so we want a continuum theory. And elements of the continuum theory, now everything from this point on is made dimensionless in a natural way. That is, with the velocity is made dimensionless by the square root of gravity and the particle diameter, for example. Making stresses dimensionless, we use the mass density of the material of the particles. So no mysteries there. As part of the dimensionalization then, we introduce a parameter sigma that is the ratio of the density of the material of the particles to the density, mass density of the gas. So this quantity for sand particles in air is about 2,000, a little more than 2,000. Okay, while if we're dealing with sand particles in water, as we did in an earlier lecture talking about debris flows, that ratio was 2.5. Okay, so in these studies, we span a large range of particle densities, specific densities. Okay, so what the point here is, we understand how to phrase the balance of, let's say, particle momentum in the flow direction. Okay, that's just the vertical derivative of the particle shear stress and versus the drag force. And similarly, the particle vertical momentum balance balances the pressure gradient with the dimensionless gravitational force. Similarly, particle fluctuation energy, we've seen a balance equation like this in what we've done in earlier studies of the kinetic theory. And particle pressure, we might say that could be related to the product of the concentration or volume fraction and a measure of the particle velocity fluctuations. Okay, so that's fine. The mystery is, what kind of a constitutive equation do we have for the particle shear stress? And what about the particle energy flux? And if we don't have any collisions, then it's likely that this guy is not going to be playing an important role. Okay, so the next couple of transparencies, I'm going to be dealing, or maybe the next transparency, I'm going to be dealing with attempting to calculate the particle shear stress, that is, constitutive relations, relating the particle shear stress to the gradient of the particle velocity, and perhaps doing something similar for the energy flux. And the way we do that is to consider individual particle trajectories. So now, here's what I'm doing. We've got a wind blowing above a bed, and at a typical, and here's the bed, and particles are flying in trajectories above the bed. And I'm interested in characterizing the component of transfer of momentum from the wind to the particles in the direction along the bed, and also to characterize the transfer of particle momentum perpendicular. So I'm curious about this, and let's say, and so I've got a component of velocity. So this is a symbol I'm using to denote velocity on the upward part of the trajectory, and I've got a component of velocity vector on the downward part of the trajectory. And as a consequence of these two velocity vectors differing because of the drag of the air on the particles, there's going to be a net transfer of momentum in the x direction. Okay? And there's also going to be a transfer of momentum in the y direction. And the way that I can begin to see that is I focus attention on the upward trajectory. So this is the x component, and instead of writing the acceleration in terms of time, I've written it in terms of the vertical coordinate, and I've used the vertical upward velocity. And similarly in the downward trajectory, I've done the same, and a minus sign appears because I'm using, again, the upward velocity here. And I'm going to make the assumption that the upward and downward velocity are the same. That is, I'm going to ignore the influence of drag on these velocities, but I'm going to take into account seriously the drag on the horizontal motion. Okay? So the idea here is that the x component, the flow component of the velocity of the particle due to the drag is much greater going downward than upward. So there's a net transfer of momentum in the x direction due to that. And the way that we kind of see how that for certain is we multiply these equations by the upward flux of particles, sum them, and average in some crude way. And if we do that, we obtain this relationship from our individual ballistic trajectory equations. And in this equation, if we make some crude assumptions, and everything I'm doing now is extremely crude. For example, I don't hesitate for a moment in taking the average of a product to be the product of averages. Okay, so I'm throwing out some what I hope are details by carrying out this crude argument. So what I say here is that this is the sum of the x components of the velocities, upward and downward. We're doing some averaging. I'm going to take the average of the products to be the products of the average, and I identify then this average with in this case, twice the average x component of velocity. That's fine. And similarly, I identify this quantity, assuming that the x and y fluctuations are the same, that the temperature is isotropic. I identify this quantity is average with the pressure, and on the right hand side I identify the flux times the change in the x velocity as being related to the shear stress. So with these identifications, and really it's a rough argument, but with these identifications I obtain a relationship in terms of variables that I'm going to regard as being continuum variables between the pressure, the upward derivative of the x component of the particle velocity, the drag on the particles, and the shear stress. And I put in a parameter alpha, which accounts for all of my sins that I've committed in obtaining this relationship. Okay, so I've succeeded in the sense that I do now have a relationship for the shear stress that will help me close the balance of momentum. And if I do the same kind of argument for not the momentum but the kinetic energy of the particles, because I've assumed that because I'm ignoring the drag on the vertical component of the motion, it turns out that the energy flux is zero. I would get a non-zero energy flux if I included the influence of the drag on the upward and downward components of velocity, because then the upward and downward components of the velocity would differ. Okay? So my energy equation is more or less empty, and I take that to indicate that the measure of the velocity fluctuations is constant through the depth of the flow. Okay. Now, okay. So now I'm going to, so the question is how good is this relationship? And the way that Alexandra has tested this relationship is he took a law of the wall turbulent shearing profile and in a numerical simulation shot particles up into it. That is, using a Maxwellian distribution for the x and y components of velocity. Okay, so this is a simulation that's possible to do. It's parameterized by the strength of the shearing, by the, well, I'll show you the results of the simulation. So we're testing how good this relationship is. And of course, the fitting parameter that we have is alpha. Okay, so here's the results of that simulation. So for an average value of u at the bed, that is for the particle phase, the particle phase inevitably slips at the bed. So what is u here? U0 is the velocity of the particle phase at the bed. And note, I mean, just for your interest, that there is a range near the bed in which the average particle velocity exceeds the velocity of the wind. Okay, that's simply a fact. Okay, so that's U0. Let's see, and what else is here? T is 20. T has to do with the the spread in the Maxwellian distribution. S, this is the Shields parameter, so this has to do with the strength of the wind. So this is some given value of what I call SH relative to the weight of the particles, a layer of particles. And what he finds is alpha has to be as large as 20, which is rather scary. And the question would be, why so large an alpha? And of course, we've made these statistical errors in equating the average of a product to the product of an average, but also we're using a drag coefficient that is good for steady drag on a particle, and the situation here is that as a particle is experiencing its trajectory, it's moving through regions of different velocities, so it's really an unsteady situation. And unsteady drags tend to be greater than steady drags, so that may be a part of it. But the fact is, we don't have a good analysis really of why that parameter alpha has to be as large as 20. Okay, but we're going to take it as 20 without further apology.
So the grains which are being ejected into the panel in the simulation, is that a point source or a line source?
Pardon me?
The grains which are being ejected in the simulation.
Yes.
So is that a point source or you're doing it?
He takes it as a point source.
And the velocity gradient which you give, you in the simulation you define bands and give beat from let us say.
Yeah. So the idea is that then, in the simulation, he calculates the shear stress at that level of the simulation.
So when you define the velocity, so 0 to h1 you give v1, and h1 to h2 v2, h2 to h3 v3, and so on. They divide it into layers to define the velocity gradient, or they do it as a function of h continuously.
No, he determines the velocity gradient numerically by dividing his simulation into strips. Okay, and then
That is the input.
but what is the input? The input are these quantities. Okay, So now, that's fine. So I've got a closure of my differential equations, if you like. Now I got to talk about what happens at the boundary. So I need boundary conditions. And here are experiments carried out by Alexandre and his colleagues in which they shoot with an air gun a particle into the bed. So it's a bed of particles, identical to the particle that they're shooting into it. And the particle rebounds. So the angle at which they shoot the particle into the bed is theta. There's a rebound and other particles. So here's the rebounding particles, and other particles, perhaps, are also knocked out of the bed. Okay? And this is exactly what you see. That is, the incoming particle is here. It rebounds, and here are ejecta that are being emitted, if you like, from the bed. Okay? There's no wind here. This is just studying the properties of the bed. And in particular, what we'd like to know is something about the rebound of the sphere that's shot into the bed, and something about the likelihood of getting ejecta, given the speed at which this guy's coming in and the inclination at which it's coming in. Okay? And that's what they've characterized from their experiments. Now I should say, this is an extreme version of the experiment, in that we're interested in steady flows. So in a steady flow, if one particle goes into the bed, only one particle can come out of the bed. Okay, so this is not representative of the problem that we're going to devote our equations to. But this is representative of situations where the wind is changing. If the wind increases, then ejecta is forced up into the wind. If the wind is decreasing, particles then revert to the bed. All right, and now I'm going to talk about their results. So first we talk about the rebounding particle. So let's see. So this is the velocity, the magnitude of the velocity of the incoming particle, the downward particle, and this is the average. This is the average velocity of the outgoing particles. Because the bed is rough, a definite velocity of incoming particle has a range of resulting rebounding particles, both in terms of velocity and in terms of angle. So that's why the average appears here. And the relationship is given in terms of a coefficient of restitution that depends upon the incoming velocity, and it depends upon the incoming velocity in this way. So these are parameters that depend at most upon the microscopic properties of the particles. The coefficient of restitution of a collision between individual particles and the coefficient of sliding friction between the particles. Okay, so that's the relationship between the magnitudes of the incoming and outgoing velocity, and then there's a relationship between the vertical components. So the vertical component of the incoming is negative, so that's why the absolute values are here. And again, the average of the y components, the relationship between the two depends upon the geometry of the collision, and this is the relationship then involving the angle of incidence and a numerical constant. Okay, so these are the rebounding relationships. And now the question is, what's the story about the ejecta? And the ejecta relation, the total number of particles ejected for a given incoming velocity is somewhat complicated. So this is the relationship governing the number of particles ejected when the dimensionless incoming velocity is greater than 40, and it involves this coefficient of restitution. If the incoming velocity is between unity and 40, then only the rebounding particle is ejected. And if the incoming velocity is below a certain magnitude, the bed captures the particle. Okay? So the three possibilities. Pardon me? This is experimental, all experimental. This is the way they've characterized the observations in their experiments. Okay? And I should say, the particles in their experiments were, let's say, in the order of 2 or 3 millimeters. Plastic beads, yeah, exactly. And then, having done that, they did discrete numerical simulations on a variety of other systems, other particle materials, other particle diameters, and that's why I could say that these results only depended upon the coefficient of restitution and the friction. They weren't functions of the density of the particles or the size of the particles. Okay, so these seem to be characteristic up to the surface properties of the materials that you're dealing with, if they're spherical. Okay, now of course sand grains are not spherical particles, and that complicates even more the situation.
So in the experiments, they have measured the velocities of the ejected particles.
Yes.
And the simulation too, they have.
Yeah, they measure the velocity of the ejected part, and they do a large number of both experimental runs and numerical simulation in order to get some statistics.
And in this EM simulation, they have measured the velocities of the ejected particles. The same thing which they have done in the experiment.
Yeah, exactly. They build the bed, which is a hard part of the simulation because these are contacting particles. They build a dense bed, shoot particles into it, track the rebound, and track the ejecta. Okay, so if you like, this is the interaction between single particles and the bed, and now we want to introduce some statistics ourselves in order to get average properties of the bed. So what we're interested in is getting the average amount of matter that is involved in these collisions. If we average over a distribution of collisions, and we'd like to characterize also the average horizontal and vertical exchanges of momentum in a collision by averaging over all possible collisions. And the question is, why would you take this velocity distribution function? Well, because it's simple, familiar, and it involves 3 parameters. It involves the number of particles, the number density of particles, It involves this measure of the velocity of fluctuation, which I indicate that is subscript 0 means at the bed, but what I've said earlier is this temperature in the bed we assume continues throughout the bed, and it involves the slip velocity or average particle velocity at the bed, and the 2 components of particle velocity. So what I'm going to do is I'm going to take this information, this velocity distribution function, and average in order to get an expression for the mass flux, and expression for the 2 components of momentum transfer at a bed. And those 3 equations are going to be phrased in terms of the average field. Well, this is the way the volume fraction is related to the number density. It's going to involve the 3 continuous fields of volume fraction, mean velocity, and velocity fluctuations. Okay, is it clear what I'm about to do? Okay, now I'm going to show you very complicated expressions that result. What? It's the velocity of the horizontal component of the particle phase evaluated at the bed. The slip velocity. Yeah. Yes.
So the distribution of the particles which are emerging from the bed is considered to be Maxwellian distribution. Is it feasible like for inelastic collisions as well, or is it like for elastic collisions?
So your first point was that the distribution of particles.
Velocities.
Yeah.
You said it is going to be Maxwellian distribution.
I say it's going to be Maxwellian, and your question is it Maxwellian? No. I mean, it doesn't deviate tremendously from the Maxwellian. For example, it's not bimodal or anything like that. But in order to close the problem, I'd like to use a distribution that involves only the continuum variables that I'm introduced already into the theory. Okay? And the Maxwellian distribution, I think, is kind of generic in terms of a 3-parameter velocity distribution function. So, if you measure in the simulation, if you carry out a full I don't know if anyone's ever carried out people are beginning to carry out full, discrete numerical simulations of particles acting with a bed. Then you could measure the distribution and see how far it deviated from the Maxwellian. But my feeling is that for our purposes, at least at the moment, it's not so terrible. Go ahead.
Is the collision elastic?
No, none of the collisions are elastic. That is, collisions between particle and particle aren't elastic, but these relationships are not elastic. That is, associated with these two collision laws, is dissipation of energy. Okay? So the wind is supplying the energy to the particles. The particles are colliding with the bed, dissipating energy, bouncing up, getting more energy from the wind, bringing that back to the bed. So that the mechanism of dissipation is this, which is a little bit more than a typical particle-particle collision, because when a particle collides with the bed, it doesn't lose energy only to the particle that it collides with. There are repeated collisions on the depth of the bed and these ejecta being shot out. So there are many mechanisms of dissipation involved in a collision of a single particle with the bed. Okay, so now we do just what I said. We characterize the mass flux by integrating that expression for n that we had over all of the incoming particles using the Maxwellian velocity distribution function. And what results is a complicated formula that involves both the ejecta and then the possibility of particles being killed if the velocity is too low. And the thing to note about this is it is given in terms of the 3 parameters of our interest, n0, t0, and u0. Okay, so it's complicated, but that's fine. And similarly, we look at the momentum flux. So we're simply looking at the change in momentum in a collision, the flux of particles coming in, all dimensionless again, and we carry out the integrals for the x component, the horizontal component of momentum, and for the vertical component of momentum. And once again, it's just integration. There's nothing mysterious about it, but the result is somewhat complicated. Okay, so that's the way. So these are boundary conditions, if you like. That is, we're regarding them as boundary conditions. And that is, here, this is the rate of collisional momentum transfer. This is the rate of vertical, horizontal momentum transfer. This is vertical momentum transfer. This is the flux of particles from the bed. And let's see. And if we identify the vertical momentum, the rate of vertical momentum to the pressure given by this relationship, that immediately gives us a relationship between the slip velocity and the fluctuation velocity, the square root of the temperature. So making this identification, or if you like, applying that boundary condition, gives us, reduces the number of parameters at the bed to 2. Okay? So that's what we are. So we've got some field equations because I've got the shear stress in a form that closes the equations. And now we've got some boundary conditions. So now we're in a position where we can phrase at least a boundary value problem for the profiles of air velocity, particle velocity, concentration. Okay, and that's, I think, what I do next. Okay. So I'm going to do a steady, fully developed flow. So that means in the steady, fully developed flow, there's no flux of particles. There's just the incoming particle and the rebounding particle. So the flux is 0. And by virtue of the flux being 0, I have another equation that I use, and that equation then determines individually values of slip velocity and granular temperature. Okay, so now I have even simpler boundary conditions. And then the shear condition, if I identify the shear stress in the flow with the rate of horizontal momentum transfer, that gives me a condition for the shear stress in the particle phase at the bed in terms of the concentration of particles at the bed and this measure of their velocity fluctuations at the bed. Okay, so I'm happy because I've got pretty clean boundary conditions and I've got a set of equations. Here's the set of equations. Here's the vertical momentum balance. I had written it earlier as dp dy is equal to minus nu, but p is the product of nu and t, and t is a constant. So this is an equation that serves to determine the way the volume fraction varies with y. Here is my constitutive equation for the shear stress in the particle phase, related to the derivative of the particle horizontal velocity, drag coefficient, and here's the balance of the horizontal momentum, and finally for the air velocity, I use the simple law of the wall, giving the vertical derivative of the air velocity in terms of y coordinate, and I put in a roughness function, or a roughness of the wall here in order to regularize this relation at y equals 0. And at the bed, I've got these beautiful boundary conditions. I take no slip of the wind at the wall, and I'll integrate over an interval up to 210 particle diameters. And I'll take the particle shear stress to be equal to 0 there. Now, if you want to ask the question of why 210, because that corresponds to a height where the particle flux is 0.001 or something like that. That is, you could phrase the top boundary in terms of some desired small particle flux. Okay, but in order to do that, you'd have to add another differential equation. So that's why I didn't do that. Okay, so I'm going to integrate these equations and see what the profiles are. Okay, and there's an integrating program in MATLAB called BVP4C. It solves 2-point boundary value problems very easily. So no problem, except I look at the system of equations and I say the boundary conditions have indicated that T is 20. And 20 put into this equation would give an exponential decay of concentration with a decay length of 20. Okay, and we know that the decay length in the experiments is twice that. Okay, so this is an indication. So I could solve that system of equation. That's great. But what this was, what that solution to the differential equation is going to give me is a decay length of 20 particle diameters. When I know, when it's quite clear, that's not the physical reality. Okay, so that raises a question of how can we repair this? How can we understand what was happening in the experiments? What mechanism is in the experiments that isn't in the theory? Okay, and the answer that we'll test is that we haven't included the possibility that suspension, direct suspension of the particles by the turbulent velocity fluctuations is playing some role. That it's generally agreed that the particles are massive enough so that turbulent velocity suspension isn't playing a role near the bed. But the strength of the turbulent velocity suspension increases, or the strength of the turbulent fluctuations increase as you go farther from the bed. So there is a possibility that far enough from the bed, this kind of suspension mechanism is possible. Okay? So the question is, how do you incorporate it into the problem? And a way to, if you were to average, let's say, the equations to account for turbulent velocity fluctuations in a way that is appropriate for compressible fluids, and this is really a compressible fluid because the mass density, average mass density of both constituents can change because the particle concentration can change. In the particle momentum equation, there's a correlation between fluctuations in concentration and vertical fluctuations in fluid velocity. Okay, and the simplest way to model that correlation is with a gradient model. So we'll adopt that. So we model that correlation as being proportional to the gradient of the average concentration with a coefficient that is related to the turbulent viscosity and the density of the fluid. And we get expressions for the turbulent viscosity in terms of the trace of the second moment of the turbulent velocity fluctuations, and in steady situations we have a formula that relates those fluctuations, the gas fluctuations, to the local shear stress. Typically those fluctuations are related to the distant shear stress, but here we recognize that it's only the total shear stress that is uniform through the flow, and the fluid shear stress is diminished from its distant value by the existence of a particle shear stress. Okay? So the idea is, let's put turbulent suspension into the problem in this way.
So that's an eddy diffusivity.
Eddy diffusivity, exactly. Yeah. That is, this is an eddy diffusivity. Okay, let's put that in. So now the problem is slightly modified. So now the pressure equation, the vertical momentum equation had another term. So here's the suspension term now in the equation for concentration. So, the good news is it looks like something's going to happen besides exponential decay with a decay length of 20. Okay, and everything else, that we can relate the turbulent diffusion to the particle shear stress. So that situation's closed. Here's the rest of it. So that's the only change we make. That's the only change we make.
What is why not?
Why not is a roughness length. So that, I mean, if we didn't have a roughness length here, this law of the wall for the turbulent velocity would be singular at the bed. Who asked the question? It would be singular at the bed. So we put in a regularizing factor that is often associated with the roughness of the bed. Okay, so we don't get singularities when we integrate at the bed. Any other questions about the system? Okay, so now I'm going to show you solutions. So I'm going to do it for two values of the Shields parameter. One slightly above the point at which no sand gets a steady solution with sand above the bed is impossible. And a value of the Shields parameter where the concentration above the bed gets so large that collisions between particles above the bed may be playing an important role. Okay? So we got our slip velocity is always the same, temperature is always the same, concentration is going to be different in these two cases. Alpha we take to be 20, and what we have here is, let's say, without suspension, we have the dashed profiles. With suspension, we have the solid profiles. So as I say, it looks like incorporating suspensions is doing us a favor with the velocity profiles, moving them at least in the right direction. All right, that's good news. Air velocity similar. Here are the profiles in the absence of suspensions, and they get moved in the other direction and much closer to the data at the two values of Shields parameter. So we're not doing anything wrong there. And finally, the concentration. All right, so here's the interesting thing, and this is what was motivating us. If we didn't have suspension, so here's this logarithmic scale again, this would be the decay that we would predict. That's the decay, exponential decay with a decay length of 20 particle diameters. If we put in suspension, suspension starts working away from the bed in a way to increase the concentration, okay? And if you're just and remember we said we don't have good data, let's say between 20 and 40. Okay, so let's just ignore this part of the profiles, and then if we try to fit, that is, so the predicted line then looks to be pretty close or far closer to the data. And in particular for the stronger wind flows, we've moved that purely exponential decay to a profile that if you wanted to fit with a straight line would have a slope far closer to 40. Okay? So having done that, we declare a victory. Thank you for your attention. Questions? More questions? Me?
The fact that the curvature of the gradient disturbance doesn't bother you.
Well, I guess the question is, would you pick up the curvature? I don't know. The prediction is moving in a different direction than the data close to the bed. Does that worry us? That might be due to collisions.
In the theory, near the bottom, close to bed, it's probably suspect as well, right? Yes.
Well, I would say if collisions are taking place, yes.
I missed how you got T0 equal to 20.
How did I get? Oh, because when I phrased the original set of equations. Okay, so I'm stuck with 20 for the dimensionless temperature. How did that come about? Okay.
You had no conduction, so there was uniform temperature drop.
Yeah. So there was no heat flux. So if you like, I assumed that the strength of the velocity fluctuations was uniform through the flow. Okay? And then I determined that value. Applying the boundary conditions. So first I got a number for this ratio, and then as soon as I said I'm going to look at steady fully developed flow, I was able to use this equation to get these numbers separately.
From the experiments.
Pardon me?
From the experiments.
Well, from an analysis that was based on the experiment. Yes. Yeah. That is, these numbers in the expressions for the momentum transfer, those numbers are inherited from these numbers. Yeah, so I'm using,
Also the gun experiment, right?
yeah, the gun experiment. So I'm using those numbers, you're right. Okay, but the point is, I saw that, I mean, I have 20 here, and I saw that if I use 20 there, the decay length is going to be 20. So I didn't even bother to solve these equations because,
The gun experiment was independent of the factor flow experiment.
yeah,
Yeah, so that's
yeah,
it's a robust thing. Right?
yes. Okay, now the way I took suspension into account, I mean, it's as rough as any piece of the analysis that preceded it.
If you go back to the equation where you are dealing with the ballistic trajectory,
With these guys.
no, even earlier, in the second or third slide, you have these ones. Top two equations. Any kind of
Yeah, this is just Newton's law. This is the acceleration. This is the x component of the acceleration parameterized in terms of space rather than time, equals the drag, the x component of drag on the particle. And this is similar. This is for the downward trajectory, but instead of using the downward or the vertical component of the downward velocity there, I've used the upward component, which I assume is equal and opposite. So that gives me the minus sign, and then that allows me to carry out this manipulation in order to get this equality in which I identify various continuum pieces. Okay?
So U is the, capital U is the free turbulent stream velocity.
Yeah, not the free surface. It's here I use capital U to denote the velocity at every point in the profile
Of the air.
of the air.
Local air velocity.
The local air velocity. Yeah. So here is profiles of U, measured and predicted. Okay. I realize that in other presentations I use it only to mean the velocity at the free surface, but here it denotes the velocity at every point through the profile.
how is the air affected by the, in which equation would be,
There's a let's see, where's S? Oh, I guess so. I don't include an equation for S because I have the idea that is this equation applies through the flow. So these guys are functions of position. Capital meaning the air velocity or air shear stress. Lowercase. Okay, so in the steady, fully developed situation, the mixture shear stress is constant through the flow, equal to its distant value. Okay, so so I know the value of the fluid shear stress as being the difference. Let me emphasize that. So I know that this is true. So what's your question? Or did I answer your question?
no, I'm saying where do you get that equation from? This is the one in the air
So this is a, let's say this is a constitutive relation. This is relating the shear stress in the fluid, to the velocity gradient of the fluid through the turbulent viscosity. And the expression for the turbulent viscosity is here.
So the x momentum balance of the mixture, it's not a pressure-driven flow, it's just the sigma x y, dy equals, z equals 0. That's a constant value. Yeah.
Okay? Yeah. And maybe I'll say one more thing. So this is a steady analysis. That's fine. What we're really interested in are the unsteady situations. And in particular, in an unsteady situation, what you're interested in is how rapidly in time or space does the flow of sand respond. So suppose I had a bed and I've got a wind above it and I have some cloud. I've got a steady cloud of grains. I've got a steady cloud of grains above it. And now let's suppose the wind increases. Because of the increase in wind, we're going to get a different cloud of grains that eventually achieves a steady state. Okay, so one thing we're interested in is what's the time necessary to go from one steady state to another steady state, let's say when the wind changes abruptly. So that's referred to as a saturation time. Okay, that's interesting. Another situation that we're interested in is the spatial equivalent of that. And that is,
Isn't there also the question of how high the suspension reaches as the extra velocity comes in?
that's also true. I mean, in the sense, I haven't captured it in the analysis that I've done because I've used a fixed thickness. But if I reformulated the problem to make my upper boundary at the point where the flux has some given small value, that point will change as the wind changes.
But it's exponentially decreasing, concentration profile.
Pardon me?
That concentration profile is exponentially decreasing anyway, right?
Yeah. So you could say, if you like.
What you want to know is how much stuff is being transported as well as you change the speed, right? So that's, you want the integral of that concentration.
Well, exactly. I mean, in fact, what people work with is they don't care so much about velocity profiles. What they care about is the flux of sand related to the Shields parameter. That's the key relations that people who work in this field are interested in. Okay, so yes, but the spatial analog of this is that suppose you have a wind blowing along let's say a region of the desert that is hard pan, no sand, and it encounters a region of the desert which is a source of sand. So then the question is, several things are going to happen. For one thing, the profile of the turbulent velocity is going to change because the roughness is changing down here at the base. But the other thing is, sand is going to begin to be entrained and diminish the velocity profile. And finally, a new steady state will be set up over the sand bed. So if this is the saturation time, this is a saturation length. Okay? And you'd like to be able to predict what that saturation length is. And that's one of the reasons that we're formulating a continuum theory, because this problem is best phrased in a continuum way, making use of, in fact, that expression for the shear stress that we derived. And why are these issues important? Well, this saturation length has much to do with whether a heap of sand will grow and eventually form into a dune. Okay, so whether that heap of sand is smaller in horizontal length or larger in horizontal length to the saturation length is going to determine whether it's dissipated by the wind or begins to accumulate and eventually develop a slip face that is characteristic of a dune. So in a sense, this is all pretty preliminary stuff, a step towards leading us to the analysis that we're really interested in, relating to or focusing on the calculation of saturation times and saturation lengths.
And you roughly orders of magnitude, what are those times and lengths?
Meters,
Oh, as sure as meters, right.
yeah.
So if the topography wasn't flat but had hills on it, that would make quite a bit of difference.
Oh yes, yes, yes. And I mean, there are regions of the desert that do not have sand. There are regions of the desert that are, I say, don't have a source of sand. There's sand within them, but sand is not sweeping down from eroding mountains. And there you get dunes of a particular nature called Barken dunes, crescent dunes. If you have sources of sand, you get dunes of other shapes. Okay, I'm finished. Thank you.